Now that we've seen how we can relate electric fields and electric potentials, we're going to be transitioning into looking at capacitors, the first of our electric circuit devices that we'll be focusing on as we transition to looking at electric circuits. Now, where I'm going to start is with a result called Kirchhoffs Loop Law. And I don't know really where else better to put it, so I'm just going to put it here. We'll be needing this as we talk about capacitors, especially when they are in electric circuits. So let's say that this is some region of space and these are equipotential contours in those regions of space, and I'm just giving them values just so we can discuss it. What Kirchhoffs Loop Law says is that if I look at any particular point, if I were to make a loop, any loop that loops back onto this point, and I add up all the changes in voltage along the loop, that will be equal to 0. So to kind of make this concrete, let's just imagine, and this is just a purely hypothetical made up in our minds loop. I maybe decide that I leave off to go from here to here and keep on going. So for this leg of the journey here, the voltage increased. Well, we went from 20 to 40, so it increased by 20 volts. And then just to maybe make things straightforward here, well, let's just say we walked along this equipotential surface here. Here, the change is 0 volts. And then maybe as I loop my way back, maybe I meander my way over here. Well, I started at 40, I went down to 30, so this is a change of negative 10 volts. And let's say I followed along this equipotential contour again, just for the funsies. This would be a change of 0 volts. And then finally, I meander my way back here. Well, now I was at 30. Now I'm at 20. This would be another change of negative 10 volts. And then say I meander my way back there. So if I were to add all this up in this example, I would have plus 20 volts, plus 0 volts, minus 10 volts, minus 0 volts, minus 10 volts, minus 0 volts for this stretch right here, and that's 0 as advertised. And this will, since the electric force is a conservative force, as long as there isn't something non-conservative messing things up here, this will always be the case, because this is essentially saying that if I were to move some test charge around in a loop and I come back to where I was, the change in the potential energy better be 0. Otherwise, the electric force isn't conservative by definition of conservative. And then if I divide that test charge back out, that's saying the same thing about the voltage. So this is a natural consequence of conservation of energy, but it's a result that we're going to be using a lot. All right, so with that, let's go ahead and introduce formally the capacitor. So schematically, we can just imagine this to be a pair of plates. So these are both plates here. And we want the dimensions of the plates to be large compared to the spacing. So this is a small spacing compared to plate size. they will hold charges, opposite charges of equal magnitude. So say if I have a charge of plus Q here, I have to have a charge of minus Q there. Now, while schematically we can just imagine two flat metal plates, let's say next to each other, a configuration called a parallel plate capacitor. What is more typical is that they have a cylindrical geometry. If you go and take a look at them, they usually look like tiny cans, a lot of times wrapped in blue insulation, although there are other colors. And the reason for the cylindrical geometry has absolutely everything to do with making it compact. The way this actually gets done is you take two thin strips of aluminized mylar and intersperse insulating material between the strips and on top of the other strip. And then you roll the whole thing up like a jelly roll. And that is basically creates a whole, more or less, it's a parallel plate capacitor, but it's been rolled into a cylindrical shape. And it's more correct to model it as a cylinder. So because the plates are large compared to the spacing, we will be able to say that inside the capacitor, the electric field is nearly uniform. Now, it turns out that there will be a little bit of field outside the capacitor, and this does matter. But we'll be talking about that in a bit. So here, in this example here, I'll have an electric field between the plates doing something like this. And for the moment, we won't sweat the fringe field too much. So if I have an electric field between the plates, this means that there has to be a voltage difference across the plates. So there we go. So this will be at a higher voltage and this will be at a lower voltage, and we know that because electric field lines like to run from high to low potential. Now this could be plus 10 and plus 5, it could be 5 and negative 5, it could be 0 and negative 10, it could be all kinds of things. But more often the negative plate will be 0, but not always. But what matters is that this voltage here is higher than this voltage here. Since the electric field is uniform and we can't change the spacing, the voltage difference across the plates is proportional to the electric field strength, but through the spacing d. So in practical application, what you're usually worried about is the voltage that's being applied, because your source of voltage, you're going to have sources of voltage like a battery or something like that. So the figure of merit that gets quoted for capacitors is cleverly called the capacitance. And figures of merit in physics are generally defined as what you get over what you had to pay. So in this case, the capacitance, which we will note with C, capital C, what you get is how much charge you're holding on the plate. This can be used in very practical application, things like, say, flashes for cameras. They require, in order for some designs of them to work, they require a huge amount of charge to go through the flash in a short amount of time. And so what the system does is it uses a capacitor to store that charge temporarily so it can then dump it all through the flash at once. Now what you had to pay, you're going to have hooked up a battery to create a voltage difference. So it'll be the voltage difference across the plates of the capacitor is what you had to pay. So the units of this are going to be coulombs per volt. And one of the things that you're going to find as we go on in electricity and magnetism is virtually every possible way that you can multiply or divide two units will end up with a new unit name. So this is a little different than mechanics, unfortunately, but it's the way it works. So a coulomb per volt is called a farad, F-A-R-A-D. And this is in honor of Michael Faraday, who did a lot of very important work on electricity and was also the person to first suggest that light was some sort of electromagnetic wave. Now, it turns out that the farad is a walloping huge unit of capacitance. So typical devices that you'll find on a circuit board will usually be in about the 1 picofarad to some number of microfarads, a few microfarads range. So remember, the pico prefix is 10 to the negative 12. For reasons I'm not entirely clear on, manufacturers usually quote picofarads and then they jump to saying hundreds or thousands of microfarads rather than saying nanofarad. I don't know why. Nanofarad's a perfectly good unit, but they don't do it. So anyway, for typical devices, picofarad to microfarad kind of range. So what you'll find on an electric circuit board. It can get up to about a farad in certain applications. For instance, a lot of computer power supplies have fairly substantial capacitors on them. And what that's designed to do is manage things like if there is a momentary fluctuation in the house power supply. In the early days of that, if there was a fluctuation, say if you had a Radio Shack TRS-80 Model 1 computer from the 1980s, you had a fluctuation in the power supply, in the power being led to the house, what was likely to happen was the computer was going to reboot on you. People figured out real quick they needed to do something about that because you don't want the computer rebooting every time the refrigerator kicks on. So capacitors started being put onto power supply boards in order to manage these temporary brownouts from things like refrigerators kicking on in the house and stuff like that. And a lot of these are actually in the like half a farad kind of range. So they're pretty substantial, but they'll fry if they're operated above a few volts. So they still don't hold an awful lot of charge, but they hold enough charge to keep the computer running during a quick little brownout just because the refrigerator kicked on or something like that. Other places where you'll see them is in if you install very large subwoofers into a car that often seems to be worth less than the subwoofers. So if you know the kind of subwoofers I'm talking about there, it turns out that because the speakers act like a giant electromagnet, one of the things that we'll see is that in order to bring everything back in phase so that the music reproduces correctly, you have to put a fairly substantial capacitor in along with it. And since these operate at higher voltages, these devices are a lot bigger than the ones you see in computer power supplies. The computer power supplies are on the order of like the size of maybe a US 50-cent piece across and maybe about a centimeter high, something like that. Whereas if you're working at higher voltages, like say 12 volts or something like that, for a speaker, it turns out that the capacitors you often use start looking like the size of a small coffee can. All this to say, a farad is a possible unit of capacitance. It does show up in certain applications, but it is an awful lot of capacitance. And you really don't want to know the kind of chemicals they have to use to make it in the insulator to make it capable of doing that. All right, so with that bit of introduction, I just want to have a quick little thought experiment here. So let's say I have here a capacitor. So what I'm drawing here is this is a wire. This is a capacitor. This is a switch, which I will close. And for now, I'll just draw a battery like this. There's a different official symbol for it, but I want us to use the, actually I want the positive terminal of the battery pointing the other way or I'll get very confused. There is an official symbol for a battery, but we'll get to that later. For now, let's imagine that I've got like a D cell or something like that here. So this would be the positive terminal of the battery. That would be the negative terminal of the battery. All right. So the first thing that I want you to think about is what's going to happen when when I close the switch. Once I close the switch, I will have completed the circuit. And with these wires here and the switch, as far as that goes, electric charges will be free to flow. Now keep in mind there is a literal physical air gap here. We can imagine it's air, but typically it's some sort of insulating material. But there is a gap here, so the charges are not free to go across this gap. All right, so when we close the switch, we have to keep in mind that a battery basically just acts like a conveyor belt for charge. So what it's going to do is we'll imagine it spinning like this, and it's going to take electrons from where they want to be over here to where they don't want to be over here. But then that means that we'll start piling up electrons over here, and we're basically just going to be making the whole electron cloud on this side of the circuit here, the wire and this plate, negatively charged. So we'll end up picking up negative charge on the plate of the capacitor and also all along the surface of the wire. Well, it'll have a bit of a gradation, but we'll get to that. And then similarly, it'll have pulled, those electrons had to come from somewhere. So the conveyor belt took them off this wire here and this plate, all merged together, sharing one giant electron cloud. And so the electron cloud here shrunk, leaving this whole area here with a positive surface charge. So we end up with our plus Q and minus Q charges on the two plates. There, we'll draw it like that. And this will continue until, so the charging will continue until the voltage across the capacitor equals the battery's EMF, which, remember, EMF was the amount of non-conservative work the battery could do per unit charge, moving charge from where it wants to be to where it doesn't want to be. All right, so then what's going to happen after that? Once we've built up enough charge here that the voltage across the capacitor is equal to the battery EMF. If we continue to let this run, what happens? Well, it's a bit of a shaggy dog story. Nothing more happens. Once it's charged, there's no more flow of charge. So we can say that a charged capacitor acts like a break in the circuit. In fact, in electric circuit design, this feature is often exploited by judicious inclusion of a device called a resistor that we haven't seen yet. You can slow up this process of charging, and you can make it take a defined amount of time. So say if you've got some part of your device that needs to be energized for a little bit in, say, a startup cycle or something like that, judiciously putting a capacitor into the circuit will allow that branch of the circuit to be energized right when you first turn the device on, and then once the capacitor builds up its charge, it just naturally deactivates that branch of the circuit. But the question is why don't we have any more flow of charge? And the answer to that is the fringe field. So let's go and take a look at extreme close-up at our two plates. So this will be my plate holding charge plus Q, and this will be my, let's make it a little closer. This will be my plate holding charge minus Q. Now, by convention, if you attach something to the negative terminal of the battery, you usually assign a voltage of 0 volts to that part of the circuit. So the voltage here is 0 volts, and then the voltage here will be equal to the battery EMF. Now, if you wanted to, you could say add 17 volts to both, because all that matters is that the difference is equal to the battery EMF. But to make the math clean, since our negative terminal is hooked up directly to the negative post of the battery, that's the usual convention most people follow. And so then here also are our wires. I'll kind of ignore the wires for just a second here, though. So what I want to think about, actually, let me just draw the wires in a different color. So what I want to, here we go. We'll just do that and that for our wire. Now, I don't want to get too far in the weeds about how the wire is going to be changing our electric potential here. If once we are fully charged, the wire is basically just part of the plate and at the same voltage. But I'm just going to kind of gloss over that and just go with our usual thing where we say that near the surface of the capacitor, the equipotential surface has to look fairly plate-like. All right. And then as I get farther and farther out, we know that the voltage is going to drift out towards 0 because it's basically going to look kind of like a dipole far away. So far away, there's going to be more of a dipole flavor to this. So farther out, the equipotential surfaces look something like this. Well, I can do a better job of drawing that one, maybe. Okay, I tried really hard. These are supposed to be symmetric. So inside the conductor, inside the capacitor, we can just follow along, and everywhere the electric field lines have to be perpendicular to the equipotential surfaces, which they are in spirit, if not in actual artwork, but that has entirely to do with me being a crappy artist. And so most of the excess charge is going to reside on these inward plates. And you can see that between the plates, the spacing of equipotential contours is quite tight, so the electric field inside is quite strong. But since the plates aren't infinite, there is a very weak electric field coming off the back sides of the plate, like so. Oops. Those should all be minus signs there. My apologies. All right, let's clean that up. Get my conductor back in there. And then make the charges all negative. All right, need to draw a couple field lines back in. There we go. That looks much better. All right, so we have a very weak electric field on the outside, but it turns out that this matters because as the battery's trying to move our electrons around, here, let's make the electron that color. Let's say you're an electron right here. So the battery is trying to pull the electron off of this plate, and it'll move it all the way around through the battery and then try to shove it onto this plate over here. So, but let's think about the electric force here. The electric field is pointing to the left, so which way is our electron going to be feeling an electric force? Yeah, to the right. So as the voltage builds up, that means the electric field strength increased both between the plates but also on the outside of the plates. And yes, this does mean that we have a very slight charge distribution on the outsides of the plates as well. But it's a lot less than on the inside in a real world capacitor. In an ideal one where you approximate it as infinite, then all the charges are purely on the inner surfaces of the two plates, and there would be no fringe field. But in the real world, there is a fringe field, and it turns out to actually matter here. Same thing here. In order to make this plate more negative, the battery would be trying to shove the charge onto the negative plate, trying to move it to the left. But again, an electron here will be feeling an electric force trying to shove it off. When the capacitor voltage is equal to the battery EMF, this is at the point where it's impossible for the battery to work any harder to shove charges in the direction that it doesn't want to go. Now, one of the things I did gloss over is, yes, the wire is a conductor, and yes, this means that the equipotential surfaces should be following along the edge of the conductor here. It makes the analysis more complicated, but the result is the same. I just wanted to put that disclaimer in before anyone roasts me on it. Alrighty, so In the next series of videos, we will be figuring out our electric potential. We'll be figuring out capacitance for different shapes of capacitors, and we'll also be figuring out how capacitors play with each other in electric circuits. Catch you then.